Nanak, and thank you for hosting us. Today we will talk to you about Containerlab, which allows you to run networking labs with Docker user experience. And before we dive into it, let's first set the stage here by understanding that networking labs or virtual networking labs are really critical today. It's our means to test things before they go into production. And they are next best thing to hardware labs or production networks. So what options do we have today to run virtual networking topologies? I would like first to start with the elephant in the room, the network emulation software projects such as EVE-NG or GNS3. They are specifically built to answer the need for building virtual networking topologies. They are proven, we know how they work, and everybody probably had some experience with one of them. They are at the same time free, you can easily download them and use, although some premium features for EVE-NG might require some extra payments. They have a nice UI which allow you to create your topology by simply drag and dropping elements on the pane and interconnect the links with the mouse, which is really nice, and it's really a human-friendly interface. But it's not all that bright in this network emulation software camp. For example, these tools are really VM-centric, which is quite understandable because the networking operating systems, they were packaged in a VMs before that. And hence, they have a weak containers support. We'll talk later more about why do we think this is very important, but for now, let's just take it as a minus here. Another thing that is not so great about them is that they are heavy and not fully open. For example, to install an EVE-NG or GNS3, you need to allocate a server or a VM, and you need to keep it running for as long as you need to run your labs. And although the UI I was just referring to as a plus, it can become as a challenge if you want to automate your networking labs. In that case, the UI is not really simple to automate. And even though that these tools have an API, it's not that really as simple as a text file that you can generate or generate with a Ginger template or something like that. What tools do we have apart from the network emulation software? We typically see that people try to reuse the VM orchestrators such as OpenStack to build the virtual networking topologies. And these VM orchestrators, they are quite common in the medium and large enterprises. So it makes sense to reuse them to deploy the networking topologies. But that's all that's good about them, because the complexity comes and takes its toll. It's really hard to use OpenStack, for example, or Proxmox, to create virtual networking topologies. It requires quite a lot of integrational effort. These tools, again, are VM-centric because they are VM orchestrators at the end of the day. And it's not even that easy to have a clean data path when you have some Linux bridges, for example, in the data path. Then protocols such as LLDP or LECP might not be really passing through those data paths. And these tools, although they have like generic UIs and CLIs, these two elements, they are not specifically built to deploy your topologies. Hence, there is no specifically built UI or CLI that can spin up a topology for you based on these VM orchestrators. And in the third bucket, there are some custom automation solutions. These are the bespoke scripts that somebody wrote, and these scripts can deploy your VMs or create containers or do whatever you want, and they can really answer the needs of you. They can be a silver bullet. But the problem with these tools is that they are really tailored for only you, and it would be really hard to make those scripts to work in a generic environment. For example, if you want to share these tools with a customer, they might have a hard time to integrate those scripts in their environment. Now, what do we gain by moving away from VMs? Because I mentioned that weak VM support was a downside of those three solutions. And when we move from VMs to containers, we, of course, essentially have containerized NOS support. And if you think that containerized network operating systems are something that doesn't really exist, it's not that true. For example, we currently have a few network operating systems which are packaged in a container format, such as Nokia SR Linux, Arista CUS, Juniper CRPD, and more will come. So having the containerized NOS support from the ground up is really important. Also, when we work with containers, we are inherently light and fast. Containers are typically consume less resources than VMs, and it's far way faster to deploy them as compared to the full-fledged VMs. Also, we work with containers and they are immutable. Hence, we can create repeatable labs because the containers will be immutable when you deploy and destroy them. At the same time, when working with containers, we can leverage all the familiar containers features. We can do bindings, we can do port exposure, we can do environment variables propagation, etc. Basically bridging the gap between the IT workloads and the networking systems. One of the most important features of containerized-based labs is that we deploy or we define the labs in the text format, such as, for example, Docker Compose. We make this really Git-friendly. So you can define your lab in declarative fashion, you can check it in Git, and somebody else can pull it out and deploy your lab. That is a really important step towards the infrastructure as code approaches. When we work with containers, we inherently work with containerized images. And now we work with images and container registries as opposed to the QCows and VDA disks. So we can, check the image of the container to the container registry without, in contrast to pushing the QCow disk to some Dropbox or OneDrive or whatever. So that makes it really easy to share the images, create the centralized store for them, and reuse them. And last but not least, making the containerized virtual networking topologies, make it really easy to use them in the CI/CD pipelines. You can deploy your virtual topologies pretty much like you would deploy your IT workloads. And again, it makes it very easy to incorporate in the CI/CD pipelines that you might have. And that's where Containerlab comes in. Containerlab is a single binary small CLI tool that allows you to deploy complex topologies such as claw topologies, and at the same time can be used with the topologies which are simple, such as back-to-back connected network instances or some arbitrary topologies that you might use. As I mentioned, it is really lightweight, it has a little footprint on the memory, and it allows you to create topologies from the CLI. And to cover the Containerlab features, I would like to invite you on a journey where we'll have 6 milestones. First, we will install Containerlab and see how easy it is to get it running on practically every operating system. Then we will get to know what Containerlab uses as its topology definition syntax. We then will deploy and manage a lab that we prepared for this talk. We will access and configure the lab nodes to let you know how you can really connect to the network operating system shells and configure them. We will work with the configuration persistency and see how we can extract the configuration from the running nodes and store them for later use. And a final step would be to package the lab and push it to a Git repository so everybody can pull it afterwards and repeat all the steps that I will show you here. Okay, so let's get going. We prepared a simple lab for you here, which is a multi-vendor lab that consists of 3 nodes. On the right-hand side, you see the GoBGP Linux container that will act as the route injector. In the center of the drawing, you see the Arista CUS, again, the containerized network operating system that acts as a route reflector. And on the left-hand side, we have the Nokia SR Linux, again, containerized network operating system that will receive the route. The timeline of events will happen like this. GoBGP announces a single route, 192.168.0.1/32, towards its only BGP peer, which is Arista CUS. Arista will act as a route reflector, and as we now know, it will bridge the gap and propagate the route towards the Nokia SR Linux. And SR Linux will receive this announcement and install it in its routing table. So that is a very simple lab, but it shows you how to create the lab, what are the topology syntax, and how you can leverage different nodes inside the topology. We start with the installation. We believe that installation needs to be really simple and easy. What you see here highlighted in dark blue color is the single installation command that you need to run to install Containerlab. That's really all it takes. And 3 seconds later, you will have Containerlab installed on your system. We support three different platforms: the Microsoft with WSL2 support, the Linux operating systems, and macOS. So you can install Containerlab on 3 of those platforms without any problems. Down below, you see a link to different installation options, because we support more than just the bash command that I highlighted in blue. We do have container with Containerlab installed. We do have packages. We do have manual installations from the code, etc., etc. So do check out all the other options if you do not feel comfortable running some bash scripts in your lab environment. Now, when Containerlab is installed, we need to understand how it works. And the way it works is that Containerlab consumes a topology file created in a YAML syntax. With this topology file, you define your lab, which consists of nodes and links. Then Containerlab takes this file and deploys those nodes on your machine. So it's really as easy as that. The basic nodes configuration is the central piece of the topology definition file. On the left-hand side, you see the file that I created for the lab, which is called rr.clab.yaml, and RR stands for route reflection. And the way you start populating these topology files is that you create a name for this lab, which is RR, and then you start putting the nodes under the topology container. So here I demonstrate a single container named SR-Linux so that I can show you what the node definition syntax is. Every node must have a name. In my case, I named my SR-Linux node very creatively. It is SR-Linux. The name of the node can be really any string that you'd like. They just need to be different. What is important to mention here is that every node must have a kind, and kind defines the flavor of the node. It allows to tell Containerlab what operating system this node will be when we deploy the lab. And with kind, we basically encode the rules how to deploy different network operating systems on your machine. Of course, since we work with containers, we need to have the container image present, and that is given with the image command here. Now, you must understand that the string that you provide here, the container image, it must be either pullable from the public Docker Hub repository or GitHub container registry or any other container registry that is accessible from the node that you run it from. So here I specify the public URL for the Nokia SR-Linux image, and Containerlab will be able to pull it. Now, let's see how we can add different nodes. We just saw that adding SR-Linux node is really easy, and it is exactly the same for CUS, for example. We specify the kind, which is CUS for the Arista CUS, and we specify the image for this node. As far as the Go BGP is concerned, we set the kind to Linux because it's a simple Linux container that we use, and this container image will use Go BGP as part of this. So this image will already have Go BGP installed. With this topology definition file that you see on the left, on the right-hand side, you see the logical view that our current topology file represents. So we have 3 nodes. We know how to deploy them. We know their kinds. But what we're missing is links. So let's get going and let's add some links to this topology. To add links is really simple. You just add a new links container to the topology file, and you specify the endpoints. So here, what we basically say is that I want to connect my SR-Linux node interface E11 to CUS interface ETH1, and that will create a VETH pair between those 2 containers. And thus, we achieve the clean data path. We create the VETH pairs between the containers, and we use this simple string representation of the endpoints to make that happen. Now, when the topology is ready, and that's really all it takes, just nodes and links, we can start and deploy the lab. Again, it is just a simple command, containerlab deploy, and we need just to refer to the topology file that we just created. And approximately 30 seconds later for this lab, you will have a summary table presented to you which say dear user, I deployed these 3 containers. They have these container IDs, they use these images, and they also have these IPv4 and v6 addresses that Containerlab assigned to them. So using this information, you will be able to access the nodes. And to access the nodes, we have several ways to do that, actually. First, as we work with containers, we can execute a process inside the container. And to do that, we will leverage the Docker CLI and its exec command. So I have 2 examples here down below, which demonstrate how you can execute the srcli process inside the SR Linux container, or you can call the bash container process inside the Go BGP container, for example. For network operating systems such as CUS, SR Linux, VMX, what have you, you of course can use SSH and connect to the SSH server that these images run. To do that, you use the SSH command, of course, and you can use either the name that the container has, such as CLab error COS in the example number 1 on the right-hand side, or you can use the IP addresses that Containerlab assigned to the nodes. That's how easy it is to connect to the nodes that have been deployed. Now, when you manage to connect to the nodes, it comes to the configuration process. And there are, of course, many ways how you can configure the nodes. You can connect to the CLI, as I explained on the slide before, and tap in your commands. Or you can use some programmatical interfaces that the nodes will have as part of their startup configuration. For example, you can use GNMI, JSON RPC, netconf, or any other APIs that the network operating systems might have as part of their config. You can also use the configuration mounts. Because you work with containers, you can mount or bind mount the file from your local system towards the container process, and you will be able to access these files and make them work as the startup configuration, for example. You can, of course, use some configuration management tools such as Scraply, Ansible, Nordnir, or your custom Python scripts, because you have network access to the nodes right out of the box when you deploy the lab. And we also have Containerlab's own configuration engine that allows you to create configurations based out of the templates and use some variables files that will be used as the variables to deploy or to template the configurations and use them when the nodes start. So let's see how that works in action, because that was quite something on the slides, but let's dive into the CLI and see how it really works. So what I have here is the virtual machine that runs Ubuntu Linux. It has Containerlab not installed yet. It has Docker installed though, which is the only prerequisite that you need to have to run Containerlab. So I wanted to first show you how easy it is to install Containerlab. To do that, you go to the containerlab.srlinux dev portal, which is our main documentation portal with lots of information around Containerlab. And here you will have the installation tab that will show you how to install Containerlab in all the different processes. So I will use the magic script that we have, which will detect the operating system and install the right package for me. So I'll just copy paste it here on my machine, and I will start installing Containerlab. It will take a couple of seconds to install it, and just like that, I have Containerlab installed and it's ready to be used. Now, what do we do when we have Containerlab installed? We need to write the topology file, as I just explained before in the slides. So here I have this topology file already created. It has the same exact content that we went through the slides. It has 3 different nodes, SR Linux, CUS, and Go BGP, and it has 2 links which interconnect these 2 nodes. Okay, so this is really what you need to have to deploy the lab. So how do you do that? As I mentioned before, all it takes is containerlab deploy -t for topology, and I refer to my topology file. Now Containerlab will take the topology file analyze what's inside it, and it will start creating the nodes. So right now you see that we created 3 containers. We created 2 links between the CUS, GoBGP, and SR Linux and CUS. And now we're running some post deploy actions for the nodes Arista and Nokia SR Linux. What we do currently is that we make sure that the nodes boot, we apply some startup configuration to them, like basic startup configuration, and 30 seconds later, we have the lab running. At this moment, you can connect to the nodes and you can start configuring them. So let me show you how you can connect to the nodes. First, I will switch to the CUS tab. That's where we will configure our Arista CUS. And I will tap and connect to the CUS. So to do that, I basically just copy the name of the CUS node, and I will do SSH admin, the name of the container. The default password is admin, and here I am already in the CUS CLI. Now what I will do here is that I will paste the prepared config for the CUS. I have it here as part of my directory that I use for this lab. There is the CUS CLI CFG file that actually has all the needed commands to configure the use case that we discussed before. So I will just copy paste those interface configuration and BGP configuration, and let me take it all. I copy it here and I paste it to my CUS CLI. Okay, my CUS configuration is done. I will do the same for the SR Linux. So again, I have the SR Linux config prepared here. It does exactly the same thing, but on the SR Linux side. We configure the interfaces, the loopbacks, the BGP, and we do this on the CLI side. So my SR Linux is here. To connect to it, I use the same SSH access. So I use the name of the SR Linux node that we have in our lab. It has the same default password, admin. Now, once I'm in, I will paste the configuration that I just copied, and boom, it's there. So what I can do right now is that I can install the watch on the show command. So what I'm interested in is that I'm interested if my SR Linux node already has some routes received from the CUS route reflector. So to do that, I will do show network instance default protocols BGP. I will leverage the highlighting features of the SR Linux, and I will check the received routes from the IPv4 address family. And this watch command will refresh every 2 seconds the show command that I just typed in, and it will tell me if I have anything received from the BGP neighbor, which I have. And I do have and I have nothing right now because there is no route reflected by the CUS at this moment. And we will come back to this output to see what happens when we will configure the GoBGP. So the GoBGP part is now our next guest. So to do the GoBGP configuration, I will use the GoBGP file that I prepared. It is a bit more involved here because we need to use the GoBGP configuration syntax. So we create the config for the GoBGP, we start the GoBGP daemon, we create the announcement, and then we will populate it. We will basically announce it through the GoBGP. But how do we connect to the GoBGP? Because it's not a network operating system, it's a Linux container. So there is no SSH server running there. So we will use the option number 1. We will actually execute a bash process inside the container of GoBGP. So the GoBGP container named clab rr GoBGP, and I will open the bash shell here. So now I'm in the GoBGP process, GoBGP container in the bash shell, and I will copy this configuration to the shell. So that's what I did here. I started the GoBGP container, GoBGP daemon, and now it is really ready to start announcing the route that we prepared. So if I do this command here, it should start announcing this thing. And now if I go back to the SR Linux, you see I have this 192.168.100.1 route received. That means that CoBGP announced the route to the CUS, CUS reflected it back to SR Linux, and SR Linux has it as part of the received routes from the CUS. So that's really the use case that I wanted to show you, that demonstrates the way how you can start working with Containerlab, how easy it is to install it, how to create a lab, although a small one, but still a multi-vendor lab with 3 different nodes, leveraging the Nokia, SR Linux, Arista CUS, and the Linux container with CoBGP stack installed. And now I wanted to go back to my presentation, and I would like to talk to you about the configuration saving process. So it's really, most of the time when you work with a lab, you dab in your commands, you create some use case, it's all good, but then you need to save it. You want to save your process so that next time you can go back to your lab and you can start not from the clean slate, but from the status that you left the lab before you shut it down. And to save the configuration manually is a tedious process if you have many nodes in your lab. So to do that, in Containerlab, we created a command, containerlab save, that will do this kind of sweep save process and save the configurations, running configurations to startup configurations on all the nodes that your lab has. So let me show you how it works. So here, if I go back to my host machine and I will use containerlab save -t for topology, and I will use my topology file that we used in the lab. And bam, in under a second, we saved running configuration to startup on both CUS node and SR Linux node. What does it mean? It means that now we save the configuration on the nodes, but that's not only just like, it's not only for the sake of saving the configuration. We need to access that configuration. And to do that, there is a thing called lab directory. Containerlab creates the lab directory for every lab that you deploy. The goal for this directory is to store all the artifacts that Containerlab might use or you might use as a user to keep some state when you work with a lab. So when you deploy the lab that has the 3 nodes that we just deployed recently, it will create a lab called clab-rr. Clab is a fixed prefix, and the rr is the lab name that you used in your topology. And inside this directory, you will have all the configurations that this node use. For example, if I now just save the configuration on my containers, I can really access it from my VM. As easy as that, I can do cat. I will go into the clab directory. I know that my CUS node is named CUS, and inside this directory there will be a flash directory. The flash directory is something that Arista creates for their persistent storage, and here you will have the startup config file created by Arista. So if we cut this file, you will see that it has all the configurations that we just tapped in through the CLI. The interfaces are configured, the BGP is configured, all the neighbors are there. And it's in this file because we just made a save from the running configuration to the persistent startup config. Now you can really take this file, copy it to someplace, check out it in Git, and it will be available to you whenever you hit save or use the containerlab save command. All right, now that was quite something. We just tapped a lot of commands. I copy-pasted, prepared configs, and we created the use case with the route reflection. But what if you want to prepare all these things, and then push it to a repository such as that your colleagues could pull it, and you do not want them to, tap those commands over and over as they want to test this specific BGP route reflection use case? Do we have any other means to do that? Yes, we do. We can have the persistent configurations mounted to the containers, and they will be used as a startup config. That is what I show here in this slide. So take a look at the left-hand side where I have the startup config command given under the SR Linux and CUS containers. What it means is that these nodes will take those files, which should be available on your machine, and they will use it as a startup config. Now, you can guess that the way it works is that you create your use case manually. You can tap those commands as I just did for the demo, and then you can save those files in some location, and you can refer to them next time you start up your lab. And then the nodes will come up already online with the config that is provided in those files. And for the Go BGP, because it doesn't have a notion of a startup config per se, we will use the Docker binds. So we will bind the Go BGP shell script that I prepared to the /Go BGP shell location inside the container. And then when you start the lab, these two guys will come with the startup config already prepared and booted. And for the Go BGP, you need to just execute this script, and it will do all its forklifting with configuring the Go BGP daemon and making the route announcement. So now this thing can be checked into the Git with all these files as a startup config and with Go BGP shell script, and anybody can pull it and replicate exactly the same stuff that I just did. And that is what I did for the repository that you see on this slide. So if you check this repository, it has all these files and all the instructions how to run it. All you need to do is just pull the container images. For Nokia SR Linux, you can use the GitHub container registry and pull it without any obligations. For COS, you would need to register with the Arista website and download the tar archive. But at the end of the day, you will be able to run this lab exactly as I just did on any machine that you have. That's really a nice thing about Containerlab. Okay, we just saw a lab which consists of containerized network operating systems. That is the prime thing for Containerlab. But we not only have containerized support, we not only have containerized operating systems that we support. Currently, we have 9 different vendors and 15 different operating systems, out of which 60% are actually VM-based nodes, and only 40 of them are containerized nodes. So that means that we can run not only containerized network operating system, but VM-based ones as well. So here I show the kinds that correspond to each vendor and the operating system that we support. And we also have this nice pictogram of a container, which indicates which image is a containerized package and which is a VM. So as you see, we have quite some support for the most common or most wanted vendors. We do not have like a sheer support for some obnoxious vendor operating systems, but still there's quite a lot of things that you can do already with Containerlab. And of course, contributions are welcome if you want to add more. Now you might wonder, how do we make VM play in the same kind of containerized field with containers? And before we made some things before we made some integrations for VMs in Containerlab, we actually used a simple Linux bridge to make sure that containers can talk to VMs. But that posed a problem, because when you have a VM that is separately deployed and containers are deployed in a topology file, there is no unification between the startup process. You can really have problems with running those as a single entity. So what we did actually is that we made sure that we can run VMs inside a container so that it can be part of the same topology file that Containerlab will take and deploy the labs. So the way it works is that we leverage the VRNetLab open source project, which allows to package a QEMU and, of course, the VM disk image inside a container. And then, as far as Containerlab is concerned, it is just a regular container. It will just spin it up, and inside it will run your usual VMX or IOSXE or what have you. So now, as I mentioned, we have a lot of operating systems already supported. And it might be challenging for you to start not knowing the ropes of the game. to make this process easier for you, we created the lab examples for practically every network operating system that we integrated with Containerlab. So if you will go to the containerlab.srlinux.dev, you will have the lab examples section in the top menu, and you will have on the left-hand side all the various labs that we created for you with different operating systems, so you can jumpstart with the operating system of your choice. Okay, so that was the pretty basic example of Containerlab, but it allowed us to, to start getting going with it. But we have, of course, ability to run more advanced labs with Containerlab, not only something small as the 3 nodes labs. And I invite my colleague Karim here to tell you more about it. So the floor is yours, Karim.
Hi. Okay, so today I'll take you through a short demo of Containerlab, a little bit more advanced, using some of Containerlab more, let's say, advanced configuration fields. So far you've seen some of the basic commands that you can use and set under a node in your topology file, such as kind, type, or the image. You also have seen a startup config to start your containers with a predefined configuration. There is also the possibility to create binds to share files from your local host to the different nodes. So those files can be shared in read, write, or read-only modes. You can also bind ports between the nodes and your host to expose services running in your nodes, whether it's GNMI servers, GNY servers, HTTP servers, if you need to. And you can see that the syntax is similar, if not exactly the same as the Docker Compose file. So that allows you to copy your existing configurations directly into Containerlab's topologies. You can also, or you have also control over the user that will spawn your container process if your image needs that. With the env field, you can set environment variables that your container can use. So if your application can use environment variables for configuration, you can set that directly into the Containerlab topology file. So this can be used, for example, to run multiple instances of the same application, or if the same node with the same configuration file, and you can customize the different instances using the environment variables. Command allows you to override the command that was set when the container was built, that allows you to further customize your images and running containers. Label field allows you to assign Docker labels to your images. That way you'll be able to query a certain subset of the nodes running in your topology, or filter the ones you don't need to have for that specific command you are running. So there's also a management IPv4 field that allows you to set a static IP as a management IP for your nodes. And a similar field exists for IPv6, management _ IPv6. The full list of configuration options is available in the link you can see at the bottom of the slide. So I encourage you to go there and read more details about them. So next, let's try to see a lab, or deploy a lab that uses some of these configuration options. So the lab I will go through today is a streaming telemetry lab using a standard streaming telemetry stack. So GNMIC as a collector, Prometheus as a TSDB, and Grafana for visualization. Console is also there, and it will be used for service registration and orchestration, and that will allow us to stitch the different telemetry stack layers together. The network topology itself will be a standard CLO topology with 2 pods, 2 spines, and 4 leaves each. And those 2 pods will be interconnected with a layer of 2 super spines. So all the nodes in this topology will be Nokia's SR Linux image using the image that's available publicly. So this topology will be deployed using GitHub Actions. So it will be triggered via push of a tag that is named a certain way, and those actions will deploy the lab and configure it on a self-hosted runner. Okay. So the whole, all the files and the configuration used in the demo that's coming next can be found in that GitHub repo listed down there. So let's have a closer look at the telemetry stack itself. So in this lab, we will have 3 instances of GNMIC running as a cluster. The 3 instances will use console for leader election and target load sharing and dispatching. Each instance of GNMIC will go and discover the nodes that are running in the topology using a Docker loader feature, which allows GNMIC to discover Docker images or Docker containers running on a specified host. These GNMIC instances will also register a Prometheus server in console and expose HTTP endpoints for Prometheus to scrape. So the Prometheus server itself will discover the GNMIC Prometheus outputs by querying the services list from console. Grafana is also part of this lab, and Grafana boots with Prometheus and a few Prometheus as a data source pre-configured, and then a few dashboards that are preloaded. There are also 4 clients, so Linux images running there connected to the leaves. So there are 4 clients. Each client is connected to a pair of leaves. So those clients are not configured in this lab, and the purpose here is to be able to generate some traffic through the leaves, send packets from one client to the other through the topology, and see what happens, and test your configurations in there. So when it comes to the network topology itself, so we have super spines, spines, and leaves. The super spines belong to the same BGP AS. Each pair of 2 spines has its own autonomous system, and each leaf is a separate autonomous system. So what I want to point out with this slide is that each spine will have 6 neighbors, and that's basically the criteria we will use to determine if our lab started successfully or not. More advanced checks can be added, of course, but for the purpose of this demo, we'll just stop at checking the number of neighbors for each of the spines. Okay. So with that, I will let's have a look at the topology itself. So by now, I think you know the different fields that Containerlab uses in a topology file. So we have the defaults here. Our default kind will be SRL. And that kind will use the SRL publicly available container image. Under nodes, we have 2 super spines, 4 spines, and 8 leaves. The super spines will be of type IXR6. The spines will use the default type, which is IXR-D3, and are all part of the group that is called spines. The purpose of the field group here is to group nodes together, and they will all have the same Docker container label called Containerlab-node-group. So that allows us to run a single command on all the spines at once. The leaves do not have any configuration under them, so they will inherit the kind and the default field. So there will be SRL of kind SRL with the default type IXRD3. As part of the topology, we also have 4 clients. Those are standard Linux images and belong to the group clients. So coming to the telemetry stack. So as I mentioned in the previous slide, so we have 3 instances of GNMIC acting as a collector. And GNMIC here is using some of the advanced configuration options I mentioned. So default kind is, or its kind is Linux, and it has a few binds here. So the first bind is mounting the default configuration file of GNMIC, where you set your username and password for your targets, where you set the subscription and the GNMI paths that you want to subscribe to. The output, in this case, it would be a Prometheus output, so you can set the type of output, the address that will be exposed to the Prometheus server. The second bind is the Docker Unix socket file. So what this allows you to do, or lets GNMIC do, is have access to the Docker API that's running on the host over the Unix socket, and allows it to discover the nodes or the containers that are running on the host. Ports here bind external and internal ports to the container. So the first port is GNMIC's REST API, which is used for clustering in this case. And the second port is the Prometheus output endpoint that the Prometheus server will scrape. So these ports are exposed and configured using environment variables. So the API, the instance name, the service address that will be registered with console, and then the address which GNMIC will listen to and that Prometheus will go and scrape. So the second GNMIC instance uses the same configuration file, but we will use the environment variable to override some of the specific configuration that the second instance needs. Here, namely, the API address or the API port, the instance name, the service address, and the Prometheus endpoint. Same goes for the third instance. So next we have the console agent. There is nothing new or nothing special here. It's just a console agent that's started, and as I mentioned before, will be used to register services and allow other nodes to discover those services. Prometheus boots with pretty much a default config. We mount this folder here that has a configuration file that specifies the different jobs that Prometheus will run, which is scraping the GNMIC instances that are running as part of the lab. Grafana uses the binds option, and we mount this data source YAML file that sets Prometheus as a data source in Grafana. We mount this dashboards.yaml file, which specifies which dashboards should be loaded on startup, and then this directory, Grafana/dashboards, contains the JSON definition of those dashboards. Then, just like with the previous lab, the list of links between the different nodes. So this lab can be started with this script, run.sh. So you can just clone this repo and run the script. You will have the whole lab up and running. But what I will do today is run it using a GitHub workflow. So this GitHub action or GitHub workflow is called deploy and will be triggered either manually if the workflow is dispatched, or if a tag starting with the letter V is pushed to the repo. What this workflow will do is install Containerlab if it's not installed, install GNMIC, deploy the lab, and then go through different configuration steps. So configuring the interfaces, sub-interfaces, routing policies, the network instance, and then BGP. All these configuration items will be pushed using gnmi set command, so gnmi set RPC. And the configuration payloads are templates that are rendered when the configuration is pushed. Once the configuration is done, we will check the BGP status for each node. If one of the nodes has BGP down, then the whole workflow will fail. And the second check we will do is checking the spines number of neighbors. If it is different than 6, then we will assume that our lab deployment failed. So I'll go ahead and so first I will check if there are any nodes running here. So there are no Docker containers running on my server. And I will just uncomment this line, which will create a second link from client 1 to the second leaf in the first pod. Before that, I will just check that the runner is still up. So my runner is registered as a self-hosted runner on the repo, and the service is up and running. So I uncommented this line. I'll go ahead and commit it. I'll push the commit. Verify that it's there. So commit is pushed. I'll create a new tag for this and then go ahead and push it, and we should see the action being triggered. So the next tag would be, let's say 013. So I'll add this tag and then push it to the GitHub repo. Okay. Let's reload. Okay, so we can see that one action was triggered. So the action deploy was triggered when this commit was pushed right now. We can go and check the different steps or what's happening in there. So we can see that it started with the actions that are defined or the jobs that are defined within this action. Installing Containerlab and gnmic were successful. It is now running the deploy lab step. So you can see here in the logs that the lab deployment was successfully done, successfully completed. You can see the full logs and the list of nodes that were deployed. The next steps would be configuration. So the first one would be configuring the interfaces, sub-interfaces, routing policies. So this is the step that's ongoing. Okay. Meanwhile, we can go and check what's happening with console and Prometheus. So if I navigate to the console web UI, I can see that a couple of services or external services are registered here. So the first one would be the gnmic API, again used for clustering. But what is interesting for us here is the Prometheus output. So each one of those gnmic instances went and registered its address that Prometheus can come discover and scrape. Let's check the Prometheus UI. So if I go to service discovery here, I can see that Prometheus discovered a couple of services, one called GNMIC internals. The second is called GNMIC telemetry. The first one is GNMIC own internal telemetry metrics or own internal metrics. The second one is the metrics retrieved from the SR Linux nodes and exposed to Prometheus. Okay, so it seems that all the workflow steps were completed successfully. We can go and check the logs of our two last steps, which are checking if our BGP is up, and the spines have exactly 6 neighbors. So it seems that we have all thumbs up. So all the BGP daemons or processes are up on all the nodes, and the BGP neighbors. So each of the spines has 6 BGP neighbors. So all BGP sessions were established successfully. If I come back to the terminal here and check the topology state, so inspect. Let's make this a little bit bigger. So we have all the nodes running in here, and we can, for example, go and double check if spine 1.1, the first spine in the first pod, the pod has all the neighbors up. So if I show the neighbors list, right, so the spine has 4 leaves as neighbors and 2 super spine as neighbors. The last step to check would be Grafana or the Grafana dashboards. It will be for 3000. Okay. So let's check the data source, if Prometheus was loaded as a data source in this Grafana instance. So we can see here that there is one data source, and that's the data source part of our topology. Second would be the dashboards. So we have 2 groups of dashboards here, GNMIC internal metrics and the SR Linux metrics. So the predefined dashboards here show the number of BGP peers that are up for each of the nodes, a few interface throughput statistics that are coming up, and the number of received routes for each of the nodes. So all this was built using the files that you can find in this repo. You can go ahead and clone it, run it locally in your machine, or run it on your own self-hosted runner. So the lab, again, combines both a telemetry stack and the topology that you're trying to instrument, but you can run this in a different way. You can run a separate telemetry lab with your favorite telemetry stack, and then point that telemetry lab to different labs that you are running on the same host or on a different host. You are not forced to combine everything in the same lab. You are able to make your labs communicate with each other, complement each other, and improve each other. Okay. I think with that, I'm done. I will hand back to Roman.
Thanks, Karim. That was quite a change from the simple 3 nodes topology lab to a 14 nodes topology with the HA for the telemetry collection, GNMIC, and all that kind of good stuff with console. We'll make sure to use the parental advisory explicit content next time you will present something like this. Okay, so let's continue with the presentation because there is something that I would like to tell you more, and that is the advanced networking options that Containerlab has. So it is quite often that that somebody asks, how can I expose a certain service in my Containerlab deployed lab if I happen to have a system that is not on the same machine as the one that runs the Containerlab? And there are a few ways that you can make this happen. First one is the exposing a service that is done through the ports command inside the topology. So because we work with containers, we can leverage the port exposure, and Containerlab, of course, can leverage that. For example, if you have the telemetry running on your nodes, and I have two nodes here on the right-hand side in the diagram, both of them running GNMI over the port 57400, I can expose those GNMI services to the host port using the port instruction right here. So I basically say my CUS node will expose port 5700 as a port 57401 on the host, and the SR Linux will expose 5700 port as the 57402 port. And by doing that, we will be able to let GNMIC to talk to those services using the IP address of the machine that these nodes are running at, and just by using different ports, because now we have like two different ports which correspond to two different nodes. And that is one of the easiest way how you can expose your lab to a third-party tool or something that runs outside of the node that hosts your container lab. But that's not only that. We also can expose the management network. Like every node that you deploy with Containerlab basically connects with its management interface to a management network. It is a simple Linux bridge that connects all those management interfaces together. So you can expose this network entirely and make it reachable to your to a system. So the user story goes here as we have the network management system that is deployed somewhere in your network, and we want to basically make this network management system to reach the nodes that you deployed with Containerlab somewhere in your network. One of the ways that you can do that is that you can create a route in the machine that hosts your network management system, and this route will say, to reach those management network that Containerlab creates, and by default we use 172.20.20 network. So we can create a route that says this network can be reached through the IP address of the machine that hosts the Containerlab. And by doing that, you will be able to stitch your NMS with your lab. So that is one of the ways. But of course, you need to have your machine that hosts your NMS to be able to configure the route here. There are ways where you can have the same kind of connectivity, but without touching the routing stack on your machine that hosts your NMS. And to do that, you can leverage the existing bridge capability that Containerlab has. What it allows you to do is that it allows you to say, dear Containerlab, when you will deploy the lab, please use the existing bridge that I have on my machine. And by doing so, the Containerlab will schedule the nodes to connect to the bridge, which is already being created by your system administrator or by yourself. And then you will be able to just address the nodes through the IP addressing that is available in your lab. And then you do not need to have a route here because your NMS knows how to reach the address that you use in the bridge, and it will just make sure that it can reach it. So that is one of the advanced ways to expose a lab that runs somewhere in your lab network without really touching any systems that are outside of your reach. And another thing that we would like to mention is that all the Containerlab is mostly about virtual networking topologies, where you deploy your topology and it has all the virtual nodes and you run your complex or simple use cases. We also wanted to make sure that you can connect some physical boxes to it. For example, there might be a traffic generator that you bought for $1 million and you want to use it. So you want to connect your traffic generator to your nodes, which are either containerized or VM in a container. How would you do that? you cannot say to Containerlab, please make sure that there is a traffic generator connected to it. But what you can do is that you can breach the interfaces of the nodes that you have part of your topology with the traffic generator. To do that, you use the breach kind, which is a special kind in the topology definition file that says these BR10 and BR20, which are of kind breach, they are actually Linux bridges. And Containerlab will use them in these endpoints configuration instructions. So what you say here is that I want my leaf1 interface E12 to be connected to the breach 10 interface L1. So this interface is really imaginary. It doesn't really matter how you name it, but it will connect the leaf1 to the breach. And then all it takes is for you to make sure that the traffic generator will be connected to the same breach. So you do your VLAN propagation or some other techniques that you use, but just to make sure that there will be L2 connectivity between this breach and the traffic generator port that you use. So by doing that, you can easily push traffic from the traffic generator all the way back to your topology that you created with Containerlab, and it will all happen magically. And of course, every lab needs to have some packet capture capabilities. Otherwise, we cannot really say what is happening on the wire. Because Containerlab uses basic Linux primitives, it is really easy to use TCP dump or Wireshark. All those points that I depicted on the left-hand side, those red dots, all these points you can tap to and sniff the traffic from. So on the right-hand side, you see the command that allows you to connect to the Containerlab host, and by just doing the classical TCP dump command and piping it to the Wireshark, you can immediately spawn your Wireshark GUI and see what is happening, what is flowing between each of those points. So it makes it really easy without any alterations to your installation, just bare Linux commands, and that will happen instantly, and you will be able to see all the traffic that floats between the points that you sniff to. All right, we are really at the end here. And I wanted to mention that Containerlab is not something that is designed to replace these great software projects such as EvenJ and GNS3. What we think Containerlab can do is to complement those. So for example, if you are more on the side of automated topology generations, if you want to be able to check out your topologies to the Git repository, and you are more on the DevOps side, then Containerlab might have more sense to you. It might provide some Git friendliness that was missing in those UI first tools, and it can enable you to make those repeatable lab builds and also make some really nice CI pipelines that will use the networking virtual topologies. It also has a very small footprint, which makes it really easy for all kinds of learning activities. So if you want to learn something new or want to get some automation experience, it is really easy to deploy just a few nodes with Containerlab and explore the yangs or the netcons of the nodes that you created without really having anything but just Docker installed and your laptop or virtual machine. At the same time, we do have fewer traditional NOSes as part of the supported images, but we still strive to have some really most wanted operating systems under our belt. And there is still no UI to Containerlab. So if you are really a UI person, you might find it problematic to use Containerlab, although the goals were to really stay simple and text-based. So if this all sounds interesting and fascinating, I have some steps for you to go next. First, of course, go and explore the containerlab.srlinux.dev site, because it has a lot of information that can help you get started or explore some advanced use cases such as Karim showed you. And most of the questions that you might have along the way, they are already been answered on this documentation portal. Then try to create a lab with the network OS that is dearest to your heart. We have support for, as I said, quite a few of them, so you will probably find a system to play with. If there is something that is missing, or you feel that you have a nice idea, please do not hesitate to reach us. You can talk to us through GitHub issues or discussions. And we also have a community server on Discord, which everybody can join and talk to us in the real time. Of course, if Containerlabs is something that really up to you and you liked it, you can give us a star and grab a Containerlab sticker at Nanak venue if you happen to be there. If you want to have some large-scale network topologies built with the same containerized flavor, you can also check the Google KNE project, which is Containerlab on steroids, where you run your labs on the Kubernetes clusters. So if you are into the big pools of nodes, do check this project. And with that, we would like to thank you for your time and see you next time. Goodbye.
Thank you very much, Roman and Karim.
Thank you.
Thank you. If we have any questions in the room? No? No questions in the room. I know you were talking to some people on the chat, so I know that there was a question that I spotted from Matthew Petak. Let me just find it. So his question was, how much memory overhead did it take to instantiate the Containerlab images?
Yeah, so typically it takes less memory on CPU for running containerized network operating systems as opposed to the VM-based packaging. And that is, of course, due to the lightweightness of containers in general and shared kernel and all that stuff. So, for example, you can run 8 nodes of either COS or SOLNX or whatever container image you use with a system that only has, let's say, 6 gigabytes of RAM and 2 vCPUs. That would be just enough, which is really small footprint if you compare it to VMs.
Excellent. Thank you very much.